Hello everyone, in this video we're going to learn about the Fibonacci sequence and how we can implement Fibonacci sequence, or how to calculate Fibonacci sequence using recursive functions and also iterative methods. Also, we're going to do a very brief analysis of like the time complexities of each method that we're going to use. So here is the very first few numbers of the Fibonacci sequence. We have 0, 0, 0, 1, 1, 2, 3, 5, and 8, up to number 55, as you see here. And that's the definition of the Fibonacci of n, which is equal to n if the number n is less than 2, and the Fibonacci of number n if n is greater than or equal to number 2 is the summation of the two previous numbers. So for example, number 2 here is the summation of these two numbers that we see here, or the number 3 is the summation of number 2 that we see here plus the summation of plus number 1 that we hear. So it's a very famous sequence. It has been used in many fields, especially like the finance. It has been found in nature, but we're not going to that. We're just going to see how we can actually implement the Fibonacci sequence in programming languages. So one way that is going to be very obvious is going to be a recursive approach, which is calling the smaller subproblems as we see here. The Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2, which is the pattern or the smaller subproblems. Again, you can watch my videos about the examples or the definition of the recursive functions. And here we have the base cases is when we have n is less than 2, then the Fibonacci is equal to n. So for n equal to 1, the value of Fibonacci is 1. For the Fibonacci of for the value of n equal to 0, the Fibonacci is equal to 0. So with this introduction, let's see that how we can implement the Fibonacci, and then again we're going to do some time analysis. So here is again a code very similar to what we're going to write in Java. So long as a return type, and it's going to be an integer, or maybe long as a parameter for the value that we're going to calculate the Fibonacci for that. So if n is less than 2, it simply returns n based on the definition that we have. And in the else statement, we'll return a call to this Fibonacci, but this time with n minus 1 plus Fibonacci of n minus 2. So and we're going to see that what's going to be the time complexity of like the Fibonacci. I will show an actual runtime on my device and see and show you the differences between different versions of the Fibonacci. So that thing is a very basic or maybe like the very primitive approach to implement the Fibonacci. But let's see that what's the time complexity of this approach. So although we are making the problem smaller, but the fact that at each step we are making the problem only making it smaller by only a factor of 1, and here by factor of 2. So if the time complexity of this Fibonacci, we call it T of n, if this is the time complexity for the calculated value of Fibonacci of n, we can see that for the n greater than or equal to 2, the time complexity is equal to the time is required to calculate the Fibonacci of n minus 1 plus the time that we need to calculate the Fibonacci for n minus 2. And this is again for let's write this one for T of 1 is equal to 1, and T of 0 also is 1. And here is because when we have n is less than 2, we only need to do one operation, which is just the return statement, or maybe we can put equal to 0, depending that which operations we're going to consider as the main operation. And here we have the So here I'm going to write for all n greater than equal to 2. So in another video, actually I have explained t of n equal to t of n minus 1 plus n minus 2 in more details, that how we can actually solve these like the equation that we have here, these time complete equations. But in general, just giving the short answer here, the time complexity will be from the big of 2 to the power n, which is a time with exponential time complexity. And for sure, any exponential time complexity is not desired. It's going to take a very long time on even the supercomputers to calculate the value. So this version, or this recursive version of the Fibonacci sequence, is not a good approach. So we're going to see that how we can actually use another technique, where in this example we're going to use the iterative approach to calculate the Fibonacci of the value n. So let's go to the definition of Fibonacci one more time. We said that the Fibonacci of n is the summation of the last two Fibonaccis. So if we want to calculate the Fibonacci of n, we can calculate all the Fibonaccis up to n minus 1, n minus 2, and keep only the last two numbers. So we don't need to keep the values for the last. And that's a problem that we have with the this recursive version. So going back again to the recursive version, that's how it's going to be the tree that will be created. So to calculate the Fibonacci of 4, we need to calculate the Fibonacci of 3 plus the Fibonacci of 2. But we know that based on the definition of the Fibonacci sequence, Fibonacci of 3 is equal to Fibonacci of 2 plus Fibonacci of 1. Already you can see that we are calculating the Fibonacci of 2 twice so far. And then Fibonacci of 2 itself is Fibonacci of 1 plus the Fibonacci of 0. So we also need to calculate Fibonacci of 1 twice. So now let's see that what's going to happen if we want to calculate Fibonacci of 5. So the Fibonacci of 5 is equal to Fibonacci of 4 plus the Fibonacci of 3. However, we have calculated the Fibonacci of 3 here once, which the program, this recursive version that we have written, will not know that. So what's going to happen that this whole calculation will be done again. So Fibonacci of 2 plus Fibonacci of 1. And again here I have to do the Fibonacci of 1 and 0. So Fibonacci of 1 plus Fibonacci of 0. So 3 times calculating the Fibonacci of 2, and twice doing the Fibonacci of 1, and again here I have to do the Fibonacci of 2 one more time plus Fibonacci of 0. So to calculate the Fibonacci of 5, I had to calculate the Fibonacci of 2 once, twice, and here 3 times. So 3 times calculate Fibonacci of 2, and then I have to calculate Fibonacci of 0, 1, 2, 3, 4, and 5, and 4 times. Also I need to calculate Fibonacci of 1 also 4 times, or 5 times if we include this one here. So that's why the time complexity of this version goes to exponential 1, because we need to recalculate the stuff that we have. So here we are not using sort of any memory to store like the already calculated value to avoid the excessive calculation. So to fix that problem, as I said, we can use actually the iterative approach. This is going to be very easy, and it's going to be just keeping the very last 2 numbers. That's because that's only what we need. So another version of like the Fibonacci, so I'm going to write long and let's call it like the Fibonacci and the I as iterative, and for the val for the n. So we're going to keep only the last two numbers, and if you look at the sequence, we know that the very first two numbers are 0 and 1. So here we're going to just write that first condition, or the base case. So if n is less than 2, just simply return n. And in the else part, we're going to write that iterative approach. So we're going to keep again the last two numbers. So I'm going to write this one maybe first. So it's going to be the very first one. So it's going to be equal to like the 0, and another variable second is going to be 1. So these are the very first two numbers of the Fibonacci sequence. Now what I need just to iterate over like the values from 2 up to n. So for integer, let's call it I to be equal to 2, and I be less than or equal to n, and increasing I by 1, because it's going to calculate Fibonacci of I 1 by 1 for all the values from 2 up to n. And again, I only need to keep the last two numbers at any step. So I can write that that the current number will be equal to the summation of the be the first plus second. So here we see that 0 and 1 gonna be that, and we're going to define first to be second. So we are replacing the first or the second last one with the new one, and then also we're going to update the second one with the current one. So I will explain on this like the sequence that how the current first and second works. I also had to define the current variable here, so current, and I'm going to set it equal to 0. And at the end, when we're done with the for loop, we just simply return the current variable, and it's going to return the actual value. So let's see with the example that how this code or this iterative code will work. So at first we have the variables first and second equal to 0 and 1. So first is equal to 0 and second is equal to 1, and we start current to be 0. So the first is 0 and the second is 1. So, and I'm going to use F and S here for just for short. So that's first and that's S, and the current is equal to, as is inside the for loop, is current equal to first plus second. So the current will be 0 plus 1, which is these two, and it's going to be 0 plus 1, we're going to be 1. Now what happens after calculating the current? We're going to assign second to be first. So this will not be the second anymore, so that's going to be our first. And as you see here, the second current will be set to second, so that's going to be also our second. So this F, the first one here that we have, will not be used anymore, because what we wanted again at any time is only the last two numbers before that number we're going to calculate. So it's go to the for loop again. So it will go to this step here, step, let's call it a step 1. So that was going to be current equal to first plus second, which is the summation of these two numbers together. So it's going to be 2, and that's going to be the current number. Again, we're going to replace first by second, so that's actually going to be like our first. So it's going to be first, so this is not going to be the first anymore. And then we're going to put the current to be also the second. Remember, at the same time, it is also the current as well, so maybe I need to just keep that. So this is or actually it's the second, so it's going to be second. So it's going to be second at the same time, which is also current. So that's going to continue until we only return the very last item, which is the current item. So, or maybe just the second, because here at the end we're assigning the second to the current. So let's see that what's going to be the time complexity of these code that we have written before actually going and testing both version of the Fibonacci's that we have implemented. So here we have for the cases that n is less than 2, we only simply return n. So if you only, in this case, only one operation. And then in the else statement, we have these two statements or three statements to assign the variable. So they are again constant. It doesn't relate to the input size, which is n. However, we have a for loop structure that goes from 2 up to including n, which is around n times, not exactly, but around or about n times we're going to do this for loop. And again, inside this for loop, we have three assignments or three statements which are going to be assignment. So we can see the number of operation is 3 times the input size, or in general we can conclude that this version of the Fibonacci will do in the big of n, which if we compare with this version that we had here, 2 to the power n is much better and much faster. And again, I will show you in the code that the differences between the actual time that they're taking on my like the laptop, and show you the differences between again the time complexities. Here is an example of the code for the Fibonacci. I changed the type of the first and second and current variables to long, just to make sure that we're not out of like enough memory to keep the very large numbers. So iterative version, if n is less than 2, it's going to return n. Else, we just simply wrote a for loop structure to use the very last 2 numbers, and at the end we're returning the current one. Here is the bad version of the bad recursive version, because we can write another recursive, but I will explain it later. So here again, the very base case is same. If n is less than 2, return n. Otherwise, it's going to return the Fibonacci of n-1 plus the Fibonacci of n-2. And here is an example of running the code. Also, I timed the amount like the actual times. So using the iterative approach from number 0 up to 47, I can just some numbers. It took less than a second to calculate Fibonacci's. However, to calculate the Fibonacci of again, this is from number 1 from the very first one to Fibonacci of 47, it took about 29 seconds, so more than 29 seconds. So for sure we can see that even for larger numbers it's going to be even worse, and as I said, using this recursive version is going to be 2 to the power n, which is not good. So this Fibonacci iterative version is going to take big O of n, this one will be big O of 2 to the power n, which is, and this is the code that I wrote again just simply just to show. This is the main method inside the Java code. You can just change the value of n to any number, and we're timing the running time to print like the 47 Fibonacci's, and also that time we need to show and calculate the Fibonacci using the recursive approach. So, but we can actually write more other versions of like the Fibonacci. We're going to see in just a few minutes. I'm going to talk about another way of writing the Fibonacci, the recursive version, which is going to be from the big O of n. That's another version of implementation of the Fibonacci sequence using a tail recursion. So what's a tail recursion? In a tail recursion, the last statement is called the recursive function again. So we created another method or function called Fibonacci recursive version 2, which is going to take an integer n, and if n is less than 2, is going to return n. Otherwise, it's going to call the recursive tail recursive function for the first time with these parameters 0, 1, 2, and n. And 2 is in this case is the index to say that which numbers we have already we're going to calculate starting with number 2 up to n. So this number 2 here is the number that we start with, and the n is the final number that we're going to calculate Fibonacci for that. And 0 and 1, as you see, are the current and last numbers. So the last two numbers are here. So inside the code, as you see here, if n is I is greater than n, return current, which means that the index I has been reached the value n, which means we have calculated all the Fibonacci values up to the value n. Otherwise, it's going to calculate or call the Fibonacci recursive version again. This time it changes the value of current and last. So the value of last will be replaced with the current, and value of current will be replaced with the current plus last. Again, which is what we have done in the iterative version, that we were keeping the very last item, or like the very last two items, first and second, and we're returning the like the current item to be the one that we have already calculated. So it's very similar to the iterative approach, with the only difference is that this one is recursive. So for sure this gonna also have the same time complexity of iterative approach, because as you see here, the number of times that we're going to call the recursive one is based on when I becomes n, because that's the condition to end functions. So I as a start with 2, and I increases, as you see in here, I increases by 1 at any time that we're calling the recursive function, and so it means that I will go up 2 to n, which gonna be again around n times. So our time complexity will be from the big O of n. So as we saw here, we can write the recursive version of the Fibonacci sequence, which also work as the same as like the iterative approach, which was big O of n. And still the very bad version of that can work in the big O of to the power n, which is not the one that we are we're dealing with. So it's going to be very easy to implement this one here. I'm not going to like show the code, but easily that's almost the actual code you need to write in order to use that or implement to execute this recursive tail recursive version of the Fibonacci. Make sure to watch my other videos, especially the one that is explaining the proof for the time to a big O of to the power n time complexity for the very primitive recursive version of implementing the Fibonacci sequence.